At the turn of the 20th century, physics was at a crossroads. For centuries, the laws of classical mechanics had provided an elegant and seemingly complete framework to understand the physical universe. From the motion of celestial bodies described by Newton to the laws of thermodynamics governing heat and energy, the scientific world, you seemed secure and predictable. However, certain experimental observations began to expose cracks in this otherwise flawless edifice. Among these anomalies, the behavior of energy emitted by heated objects, particularly blackbody radiation, stood out as a profound challenge. The classical theories, including the Rayleigh-Jeans law, predicted results that diverged drastically from experimental data, especially at higher frequencies. This contradiction became known as the ultraviolet catastrophe, and it was a puzzle that threatened to undermine the foundation of physics as it was understood. Enter Max Planck, a German physicist born in 1858 in Kiel, into a world that revered Newtonian mechanics, but increasingly grappled with the limits of its explanatory power. Planck was initially trained in classical physics, steeped in the traditions and methods that had defined scientific inquiry for generations. He had studied under some of the most prominent physicists of the era, and had a deep appreciation for the elegance and precision of mathematical formalism. Yet, Planck's genius lay not merely in mastery of existing knowledge, but in his willingness to challenge it when reality demanded it. The problem of blackbody radiation presented exactly such a challenge. Experimental data showed that the energy radiated by a perfect absorber of light did not conform to the smooth, continuous distribution predicted by classical physics. At low frequencies, classical formulas seemed adequate, but at high frequencies, they diverged to infinity, a physically impossible result. Planck approached this dilemma with meticulous care. Unlike some of his contemporaries who were eager to discard classical theories wholesale, Planck sought a solution that would preserve the rigor of established principles while accommodating the stubborn anomalies in observation. Through a combination of mathematical insight and physical intuition, he proposed a hypothesis so radical that it would shake the very foundations of physics. Energy is not continuous, as previously believed, but is instead emitted or absorbed in discrete packets, which he called quanta. This idea was profoundly revolutionary because it defied centuries of accepted wisdom. Up until this point, energy, like matter in classical mechanics, was considered a smooth and continuous quantity. Planck's quantization implied that at the microscopic level, nature operates in jumps rather than a seamless flow, a concept that would fundamentally alter humanity's understanding of the universe. Planck's introduction of the quantum of action, now known as Planck's constant h, provided the numerical framework to describe these discrete energy exchanges. His formula for blackbody radiation, expressed mathematically in terms of frequency, temperature, and Planck's constant, accurately matched experimental observations across the entire spectrum. This achievement was not merely a minor correction to existing theory. It represented a profound conceptual leap. Planck's law resolved the ultraviolet catastrophe by demonstrating that high-frequency radiation is naturally limited because energy can only exist in quantized amounts. In other words, an object cannot emit arbitrarily small fractions of energy at high frequencies. It can only emit whole quanta, corresponding to specific energy packets. This insight marked the birth of quantum theory, the cornerstone of modern physics. The impact of Planck's work cannot be overstated. While his initial motivation was to solve a specific problem in thermal radiation, the implications of quantization extended far beyond that narrow scope. Planck himself was initially cautious in interpreting his hypothesis, viewing it as a formal mathematical device rather than a literal description of nature. However, this cautious approach belied the revolutionary power of his discovery. By quantizing energy, Planck opened the door to a new era in physics, one in which classical intuitions about continuity and determinism would gradually give way to probabilistic and discrete models of reality. Subsequent physicists, most notably Albert Einstein, Niels Bohr, and Werner Heisenberg, built upon Planck's foundation to develop the full edifice of quantum mechanics. Einstein, for instance, applied Planck's quantum hypothesis to explain the photoelectric effect, demonstrating that light itself consists of quantized particles, photons. Bohr used quantization to model atomic structure, explaining the discrete energy levels of electrons in hydrogen. Heisenberg and Schrödinger later developed the formal mathematical frameworks of quantum mechanics that underpin modern physics, all tracing their origins to Planck's seminal insight. Planck's revolutionary work also had profound philosophical implications. By demonstrating that energy is quantized, he forced scientists to reconsider the very nature of reality at a microscopic level. Classical physics, rooted in determinism, suggested that the future state of a system could be precisely predicted given complete information about its present. Quantum theory, beginning with Planck's insights, introduced inherent limits to this predictability. The microscopic world was no longer a smooth, continuous landscape, but a discrete, probabilistic realm where certainty was replaced by probability distributions, and the act of measurement itself could influence outcomes. Planck's discovery thus not only solved a technical problem in physics, but also initiated a fundamental rethinking of the nature of knowledge and observation, a philosophical revolution as significant as the scientific one. The historical context of Planck's discovery is also significant. At the time, Germany was a hub of scientific research and intellectual rigor. Universities like Berlin and Göttingen fostered a culture of mathematical precision and theoretical exploration. Planck, working primarily at the University of Berlin, was part of a community of scholars dedicated to pushing the boundaries of knowledge. Yet, despite the vibrant scientific environment, the idea of quantization was so foreign that it initially met with skepticism. Planck himself viewed his hypothesis cautiously, aware of its radical implications. It would take years before the broader scientific community fully recognized the depth of his contribution. In many ways, the delayed acceptance of Planck's ideas highlights the tension between tradition and innovation, a tension that is central to the story of scientific progress. Moreover, Planck's approach exemplified a unique blend of careful empiricism and bold theoretical thinking. He did not abandon the principles of classical mechanics lightly, nor did he propose quantization as a purely speculative idea. Instead, he derived his hypothesis from precise experimental observations, guided by mathematical formalism and constrained by physical reasoning. This methodological rigor helped ensure that quantum theory would not be dismissed as mere speculation, but would instead gain credibility as a fundamental scientific principle. The precision of his equations and the accuracy of his predictions laid the groundwork for the widespread acceptance of quantum mechanics in the decades to come. Planck's work also underscores the importance of intellectual courage in scientific discovery. To propose that energy is quantized at a time when classical physics reigned supreme required a willingness to challenge deeply entrenched assumptions. Planck's readiness to follow the evidence where it led, even when it contradicted conventional wisdom, exemplifies the qualities of a true revolutionary thinker. It reminds us that progress often comes not from incremental improvements, but from radical reconceptualization, a willingness to see the world differently and to question the foundations of established knowledge. In retrospect, Planck's first keynote achievement, the introduction of quantum theory, was not merely a technical innovation. It was a seismic shift in human understanding, comparable to the revolutions initiated by Copernicus, Galileo, and Newton. By showing that energy is quantized, Planck revealed a hidden order in the apparent chaos of thermal radiation, a discrete architecture underlying the continuum of the natural world. This insight transformed physics from a science of continuous flows and deterministic laws into one capable of describing the discrete, probabilistic, and profoundly counterintuitive phenomena of the atomic and subatomic world. Even today, the legacy of Planck's work is omnipresent. The technologies that define modern life, semiconductors, lasers, magnetic resonance imaging, quantum computers, are all built upon principles that trace directly back to the concept of quantization. Without Planck's revolutionary insight, the digital age, modern medicine, and the information revolution might have unfolded very differently. His introduction of quantum theory stands as a testament to the power of curiosity, mathematical reasoning, and the courage to challenge the limits of understanding. The introduction of quantum theory by Max Planck was not merely an isolated breakthrough in thermal radiation. It was the spark that ignited a series of intellectual revolutions across the physical sciences. The profound nature of this shift cannot be overstated. Classical physics, despite its elegance and predictive power, was fundamentally rooted in the concept of continuity. Whether describing the flow of fluids, the motion of planets, or the oscillations of molecules, the assumption was that physical quantities could vary smoothly without interruption. Planck's insight that energy is quantized shattered this core assumption. For the first time, a fundamental property of the universe was understood to exist in discrete steps rather than a seamless continuum. The immediate implications for physics were both subtle and profound. While Planck initially regarded his idea of quantized energy as a formal mathematical tool rather than a literal description of nature, others quickly recognized its potential to explain a range of phenomena that classical physics could not. Albert Einstein's work on the photoelectric effect, for example, directly applied Planck's quantum hypothesis to light itself, demonstrating that photons, discrete packets of electromagnetic energy, could eject electrons from a metal surface. This was a conceptual leap that extended the principle of quantization from the thermal realm into the domain of light, bridging the gap between matter and radiation in a fundamentally new way. Planck's idea had thus laid the foundation not only for quantum mechanics, but also for quantum electrodynamics, the theory describing interactions of light and matter. Niels Bohr further extended Planck's insights to the structure of the atom. By quantizing the energy levels of electrons orbiting a nucleus, Bohr could explain why atoms emitted light at specific frequencies rather than a continuous spectrum. This accounted for the observed spectral lines of hydrogen and provided a coherent explanation for atomic stability, a problem that had puzzled scientists for decades. Bohr's model, while later refined by the full formalism of quantum mechanics, was conceptually rooted in Planck's revolutionary notion of discrete energy levels. In this way, Planck's first keynote contribution cascaded across multiple subfields, influencing not only thermodynamics and radiation, but also atomic physics and the emerging understanding of matter itself. The philosophical implications of Planck's discovery are equally striking. Classical determinism held that if one had perfect knowledge of a system's initial conditions, its future could be predicted with certainty. Planck's quantization introduced a fundamentally different world, in which continuity and certainty gave way to probabilistic behavior at microscopic scales. This probabilistic nature of reality, fully developed in the work of Heisenberg, Schrödinger, and Dirac, stems from the initial recognition that energy exchanges occur in discrete, quantized units. It forced physicists and philosophers alike to rethink the nature of reality, observation, and knowledge itself. The world, once conceived as a smooth and continuous clockwork, now revealed hidden granularity at its very core. The historical context of Planck's work also amplifies its significance. Planck was working at the University of Berlin during a period of intense scientific development. German universities were hubs of intellectual rigor, emphasizing mathematical precision and theoretical depth. However, proposing a concept as radical as quantized energy was inherently risky. Planck's careful approach, grounding his ideas in empirical data and rigorous mathematics, enabled him to introduce a concept that might have otherwise been dismissed as speculative. His combination of bold creativity and disciplined methodology set a model for scientific innovation that endures to this day. Moreover, Planck's work exemplifies the cumulative and collaborative nature of science. While he originated the quantum hypothesis, its full implications were realized only through the contributions of subsequent physicists. Einstein, Bohr, Heisenberg, Schrödinger, Dirac, and countless others expanded, refined, and applied Planck's insights in ways he had not originally envisioned. This collaborative evolution highlights the way transformative ideas propagate through the scientific community, inspiring new lines of inquiry and generating technological innovations that transform society. Speaking of societal impact, the practical consequences of Planck's first keynote discovery are immense. The quantization of energy underpins nearly every modern technological innovation. Semiconductors, which power computers, smartphones, and nearly every electronic device, rely on principles of quantum mechanics derived from Planck's initial insight. Lasers, essential in telecommunications, medicine, and manufacturing, exploit discrete energy transitions in atoms, again directly connected to Planck's theory. Even medical imaging techniques, such as MRI and PET scans, are built upon quantum principles, highlighting the profound, real-world significance of what began as an abstract theoretical proposal. Planck's work illustrates the fascinating journey from fundamental theory to practical application, a journey that defines much of modern science and technology. Planck's personal dedication and resilience also amplify the significance of his work. He lived through an era marked by political upheaval, war, and personal tragedy. Both world wars affected Germany deeply, and Planck's family experienced immense hardships. Despite these challenges, he remained devoted to the pursuit of knowledge, emphasizing intellectual integrity and the search for truth above personal gain or comfort. His perseverance serves as a powerful reminder that scientific progress often requires not only intellectual brilliance, but also moral courage and resilience in the face of adversity. The ripple effects of Planck's quantum theory continue to this day. Modern quantum mechanics, quantum computing, quantum cryptography, and particle physics, all of these fields trace their conceptual ancestry to Planck's discovery of energy, quanta. The ongoing exploration of fundamental particles and the search for a unified theory of physics are, in many ways, extensions of the questions Planck first raised. His insight into the discrete nature of energy remains a guiding principle in our quest to understand the deepest workings of the universe. Furthermore, Planck's work reshaped our approach to teaching and conceptualizing physics. Textbooks, curricula, and research programs across the globe now center quantum theory as a foundational concept, illustrating how a single insight can redefine an entire discipline. Young physicists are introduced early to Planck's constant Blackbody radiation and the notion of quantization, embedding the revolutionary ideas into the very fabric of scientific education. The educational impact ensures that Planck's first keynote continues to inspire curiosity and intellectual exploration for generations. Finally, the revolutionary nature of Planck's work lies not only in the equations or the constants he introduced, but in the fundamental shift in perspective he enabled. He revealed a universe that is not entirely continuous, predictable, or classical, but one that contains discrete elements, probabilities, and hidden complexities. The recognition that reality itself is quantized at its most fundamental level challenges our intuitive understanding and encourages a mindset of exploration, humility, and wonder. Planck's light, indeed, changed physics forever, not just by solving a problem, but by transforming how we see and interact with the universe. At the dawn of the 20th century, physics appeared to be a nearly complete discipline. Classical mechanics, developed by Isaac Newton centuries earlier, had provided a coherent framework to describe the motion of planets, the dynamics of forces, and the principles governing everyday objects. Thermodynamics had codified the rules of heat and energy transfer, while Maxwell's equations unified electricity and magnetism into a single elegant theory. This body of knowledge gave scientists the sense that the universe was not only comprehensible, but also fundamentally deterministic, a vast, predictable clockwork in which every effect had a calculable cause. Yet, despite these remarkable achievements, cracks were beginning to appear in the edifice of classical physics. Experimental evidence accumulated that defied explanation by existing theories. One of the most pressing of these challenges was blackbody radiation, the way objects emit light and heat when heated. Classical physics predicted that as an object's temperature increased, it would emit an ever-growing amount of energy across all frequencies. According to the Rayleigh-Jeans law, the intensity of radiation at high frequencies should increase without bound, theoretically approaching infinity. Physicists quickly realized that this prediction was impossible. An infinite output of energy from a finite object contradicted physical reality. This glaring inconsistency became known as the ultraviolet catastrophe, highlighting the urgent need for a new theoretical framework. Blackbody radiation was far from the only anomaly. The photoelectric effect, in which light striking certain metals causes the ejection of electrons, also confounded classical theories. Experiments revealed that below a specific frequency threshold, no electrons were ejected regardless of the light's intensity. Classical wave theory predicted that energy should accumulate continuously and eventually liberate electrons, making the observations inexplicable. Similarly, the discrete emission spectra of atoms posed a direct challenge. When elements were heated or subjected to electrical discharges, they emitted light at specific frequencies rather than a continuous spectrum. Classical electrodynamics offered no mechanism for these discrete energy levels, leaving a critical gap in understanding the structure and behavior of matter. It was into this landscape of unresolved problems that Max Planck stepped. Born in 1858 in Kiel, Germany, Planck was trained in the classical traditions of physics, immersed in the mathematical rigor and empirical methods that had dominated the field for centuries. Unlike some of his contemporaries who might have sought to discard classical theory entirely, Planck approached the problem with a unique combination of reverence and skepticism. He recognized the immense success of Newtonian mechanics, thermodynamics, and electromagnetism, yet he was not blinded by tradition. He understood that the anomalies in blackbody radiation and related phenomena represented genuine challenges that could not be ignored or explained by incremental adjustments to existing theories. Planck's approach was rooted in careful observation, meticulous calculation, and deep physical insight. He examined the experimental data on blackbody radiation, noting the precise ways in which it diverged from classical predictions. At low frequencies, classical formulas seemed reasonably accurate, but at high frequencies, the divergence was dramatic. The Rayleigh-Jeans law, which predicted energy density proportional to the square of the frequency, suggested that objects should emit infinite energy in the ultraviolet region, a conclusion clearly at odds with experimental reality. Many physicists of the time were aware of this ultraviolet catastrophe, but few could conceive of a solution that preserved the integrity of established physics while addressing the anomaly. Planck's genius was to recognize that solving this problem required a radical reconsideration of the nature of energy itself. The limitations of classical physics were not merely technical. They represented a fundamental philosophical dilemma. Classical theories assumed continuity, continuous energy distributions, continuous motion, and smooth transitions. Energy was thought to flow without interruption, and nature itself was assumed to be infinitely divisible. Planck's problem highlighted that these assumptions might not hold at microscopic scales. The failure of classical physics in explaining blackbody radiation, discrete atomic spectra, and the photoelectric effect suggested that the continuum model of energy was incomplete. The stage was set for a revolutionary idea. Perhaps energy itself is not continuous, but exists in discrete quantities. This realization marked a pivotal moment in the history of science. Classical physics had dominated the previous centuries, providing not only predictive power, but also a philosophical worldview of determinism and continuity. Yet, the anomalies confronting Planck and his contemporaries revealed that nature harbored deeper complexities. The gap between theory and experiment was not a minor discrepancy. It was a fundamental crisis, threatening the very credibility of the classical framework. Physicists recognized the need for a new approach, one that could reconcile empirical observations with theoretical consistency. Planck's work would ultimately provide that approach. Planck's methodology in addressing the limitations of classical physics was exemplary. He did not immediately discard classical laws, but sought a general principle that could encompass both low and high frequency behavior. He introduced the concept of quantized energy as a formal mathematical solution to the blackbody problem. By proposing that energy is emitted or absorbed in discrete units proportional to frequency, Planck's model accurately described the observed radiation spectrum. This idea, seemingly minor at first, represented a seismic shift in thinking. It preserved the predictive power of classical laws where they applied, but introduced a fundamental departure where classical physics failed. The broader implications of Planck's intervention in the limitations of classical physics were profound. By identifying where classical theories broke down, Planck paved the way for the development of quantum mechanics. The very act of questioning the completeness of classical physics inspired a generation of scientists to explore the atomic and subatomic worlds in ways that had previously been considered speculative. Planck's insight suggested that the universe at its smallest scales operates according to rules distinct from those observed at macroscopic scales, a realization that would shape modern physics for decades to come. Moreover, Planck's work illustrates the importance of anomalies in scientific progress. The failures of classical physics did not represent mere inconveniences. They were opportunities for profound discovery. By confronting the inability of existing theories to explain empirical observations, Planck identified a pathway to a deeper understanding of nature. His solution, quantized energy, demonstrated that anomalies are not obstacles to be ignored, but signposts guiding scientists toward revolutionary ideas. The consequences of recognizing the limits of classical physics extended beyond Planck's own work. Albert Einstein applied Planck's quantization to the study of light, explaining the photoelectric effect and introducing the concept of photons. Niels Bohr used these principles to model atomic structure, accounting for discrete energy levels. Werner Heisenberg and Erwin Schrödinger formalized quantum mechanics, providing a comprehensive theoretical framework that resolved many of the outstanding paradoxes of classical theory. Each of these developments can be traced back to Planck's initial recognition that classical physics could not explain certain phenomena. Historically, Planck's work occurred during a period of intense intellectual ferment. The late 19th and early 20th centuries were a time when scientific traditions were being questioned across disciplines. In physics, the anomalies challenging classical theory mirrored similar shifts in mathematics, philosophy, and biology, where previously accepted ideas were being reevaluated. Planck's recognition of the limitations of classical physics was thus part of a broader cultural and intellectual movement, reflecting a willingness to confront established paradigms and explore new conceptual territories. The impact of Planck's insight into the limitations of classical physics is not confined to theory alone. It has practical ramifications in technology, education, and research. Quantum theory, born from the recognition of these limitations, underpins semiconductors, lasers, MRI machines, and quantum computing. The educational structures of physics now incorporate the story of classical physics failures as a crucial teaching point, illustrating how empirical observation drives theoretical innovation. By confronting the limits of classical theory, Planck not only solved a specific scientific problem, but also established a model for how science progresses, through careful observation, recognition of anomalies, and the bold introduction of new principles. Max Planck's most revolutionary insight was the idea that energy is not continuous, but exists in discrete packets, which he called quanta. This concept, introduced in 1900, marked a fundamental departure from classical physics and laid the foundation for the entire field of quantum mechanics. To understand the significance of Planck's proposal, it is necessary to consider both the scientific context in which it arose and the profound implications it had for the understanding of nature. At the turn of the 20th century, physicists were struggling to explain the phenomenon of blackbody radiation, the way objects emit light when heated. Classical theories, based on the assumption that energy could vary continuously, failed to match experimental observations. High-frequency radiation predicted by classical laws, specifically the Rayleigh-Jeans law, diverged toward infinity, a contradiction famously called the ultraviolet catastrophe. Scientists could measure the energy emitted at different frequencies, but existing theories could not reconcile the data, especially in the ultraviolet range. Planck's brilliance was to confront this problem with a bold and unconventional idea. Instead of modifying classical equations incrementally, he proposed that energy could only be emitted or absorbed in discrete amounts. Each packet of energy is proportional to the frequency of the radiation, expressed mathematically as E equals h nu, E equals h backslash nu, E equals h nu, where E is the energy of a quantum, nu backslash nun, U is the frequency, and HHH is Planck's constant, a new fundamental constant of nature. This was an astonishing suggestion because it implied that energy, a quantity previously thought to flow smoothly and continuously, could only exist in specific, indivisible amounts. Planck initially introduced quanta as a mathematical device to make his blackbody radiation formula fit experimental results. He was cautious about its physical interpretation, viewing it as a formal solution rather than a literal description of nature. However, the consequences of this hypothesis quickly became apparent. By quantizing energy, Planck not only solved the ultraviolet catastrophe, but also established a framework for understanding phenomena that classical physics could not explain, including the photoelectric effect, atomic spectra, and, eventually, the behavior of subatomic particles. The idea of energy quanta fundamentally changed the way scientists conceptualized the microscopic world. In classical physics, energy could be divided indefinitely. Any small fraction of energy was theoretically permissible. In contrast, Planck's quanta introduced a fundamental granularity to nature. Just as matter is made of atoms, energy itself is quantized, composed of discrete units. This insight bridged a gap between matter and radiation, suggesting that both follow specific, quantized rules at microscopic scales. The implications of Planck's quanta were far-reaching. Albert Einstein expanded on this concept in 1905 by proposing that light itself is made up of quanta, later called photons. Einstein used this idea to explain the photoelectric effect, demonstrating that light must transfer energy in discrete packets to dislodge electrons from metal surfaces. Niels Bohr applied Planck's principle to atomic structure, showing that electrons could occupy only certain discrete energy levels. Transitions between these levels involved the absorption or emission of energy quanta, explaining the discrete spectral lines observed in experiments. In this way, Planck's simple yet radical idea provided the foundation for a new understanding of atomic and subatomic phenomena. The introduction of quanta also had profound philosophical consequences. Classical physics portrayed the universe as continuous, deterministic, and predictable. Planck's discrete energy units suggested that, at fundamental levels, nature operates in jumps rather than smooth transitions. This concept challenged centuries of scientific assumptions and required a re-evaluation of basic principles about reality, measurement, and causality. Quantum theory, which grew directly from Planck's work, would later reveal that probability and uncertainty are intrinsic properties of the microscopic world. Technologically, the recognition of quanta has transformed human life. Semiconductors, lasers, quantum computers, and MRI machines all rely on principles derived from energy quantization. Every photon of light used in fiber optic communications, or every electron manipulated in a transistor, embodies the reality of Planck's quanta. His idea, initially a theoretical solution to a specific problem in radiation, became the cornerstone of modern physics and the digital age. Planck's insight also highlights the nature of scientific innovation. It demonstrates how careful observation, combined with the courage to challenge fundamental assumptions, can lead to revolutionary breakthroughs. By asking whether energy is truly continuous and daring to propose an alternative, Planck changed not just physics, but the way humans understand the universe. His work is a testament to the power of curiosity, intellectual rigor, and the willingness to think differently about even the most basic aspects of reality. Max Planck's introduction of the quantum of energy not only solved the puzzle of blackbody radiation, but also led to the discovery of a new fundamental constant, now known as Planck's constant. Denoted by HHH, this constant became one of the cornerstones of modern physics, providing the quantitative framework for understanding phenomena at atomic and subatomic scales. Its introduction marked a paradigm shift, embedding the concept of quantization into the very structure of physical law. Before Planck, physics was dominated by continuous models. Energy, like matter, was assumed to vary smoothly. Newton's mechanics, Maxwell's electromagnetism, and the laws of thermodynamics all relied on this assumption of continuity. Yet, as Planck studied the radiation emitted by a blackbody, he observed that classical formulas could not match experimental results at high frequencies. To reconcile theory with observation, Planck proposed that energy is emitted or absorbed in discrete amounts, with the energy of each quantum proportional to the frequency of radiation. E equals h nu E equals h backslash nu E equals h nu. The proportionality constant HHH became Planck's constant, a fixed number that would later be recognized as a universal feature of nature. The significance of Planck's constant lies not only in its numerical value, but also in its conceptual role. By defining the size of energy quanta, HHH introduced a scale at which quantum effects dominate. It is extraordinarily small, approximately 126 times 10 minus 3, 146, 126 backslash times 10 minus 34, 126 times 10 minus 34 joule seconds, explaining why classical physics works so well at macroscopic scales. The tiny magnitude of HHH allows the continuous approximations of classical mechanics and electromagnetism to remain valid for everyday phenomena, while simultaneously governing the discrete processes that occur at microscopic scales. In essence, Planck's constant bridges the macroscopic and microscopic worlds, defining a fundamental threshold between classical and quantum physics. Planck's constant also became the foundation for several key developments in theoretical physics. Albert Einstein, in 1905, used HHH to explain the photoelectric effect, demonstrating that light consists of discrete photons, each carrying energy E equals h nu E equals h backslash nu E equals h nu. This work earned Einstein the Nobel Prize and provided one of the first independent confirmations of Planck's quantum hypothesis. Niels Bohr applied the concept to atomic structure, using Planck's constant to calculate the discrete energy levels of electrons in hydrogen atoms. Bohr's model accurately predicted the spectral lines of hydrogen, showing that the emission and absorption of light by atoms occurs in quanta directly proportional to HHH. Moreover, Planck's constant became central to Heisenberg's uncertainty principle, formulated in 1927. The principle states that it is impossible to simultaneously determine a particle's position and momentum with arbitrary precision. The uncertainty is quantitatively expressed using HHH, linking the inherent limitations of measurement to the fundamental granularity of energy and action. This shows that Planck's constant is not merely a number, but a deep reflection of nature's structure, governing the probabilistic behavior of particles at quantum scales. In addition to its theoretical importance, Planck's constant has profound implications for technology. The principles derived from HHH underpin semiconductors, lasers, and modern electronics. Every transistor in a computer, every photon in a laser, and every measurement in quantum metrology is ultimately governed by Planck's constant. Without it, quantum mechanics, the theory that explains the stability of atoms, chemical bonding, and the behavior of electrons, would lack its quantitative foundation. Planck's constant provides the bridge between abstract theory and practical application, making it one of the most impactful constants in science. The philosophical implications of Planck's constant are equally profound. By defining the minimum action that can occur in nature, HHH challenges classical intuitions about continuity and determinism. It shows that the universe has an inherent granularity, a built-in discreteness that limits the precision of energy and motion at fundamental scales. This insight forced physicists to rethink long-held assumptions and embrace a new probabilistic world view, fundamentally altering the scientific conception of reality. Planck's constant also provides a unifying thread through multiple branches of physics. From quantum mechanics to quantum field theory, from atomic physics to particle physics, HHH appears as a central parameter governing energy, frequency, and action. Its universality reflects the consistency of physical law across scales and phenomena, reinforcing Planck's role as a pivotal figure in shaping modern scientific thought. Furthermore, Planck's constant has become so essential that it is now a defining element in the International System of Units, (C). In 2019, the kilogram was redefined in terms of HHH, linking mass to a fundamental constant rather than a physical artifact. This decision underscores the profound influence of Planck's discovery not only in physics, but also in metrology, technology, and scientific standards worldwide. Planck's introduction of this constant also exemplifies the interplay between observation, theory, and mathematical rigor. He derived HHH by carefully fitting his blackbody radiation formula to experimental data. Unlike speculative hypotheses, this constant was empirically grounded, demonstrating the power of combining precise measurements with theoretical insight. It highlights a broader lesson in science, that fundamental constants, once identified, become the backbone for entire frameworks of understanding, guiding both theoretical exploration and practical application. In summary, Planck's constant is far more than a numerical value. It is a conceptual cornerstone of modern physics. It quantifies the discrete nature of energy, defines the scale at which quantum effects dominate, and provides the foundation for both theoretical developments and technological innovations. From solving the ultraviolet catastrophe to enabling quantum mechanics, lasers, semiconductors, and redefining the kilogram, Planck's constant embodies the enduring significance of Max Planck's work. It is a symbol of the revolution he ignited, a revolution that continues to shape science, philosophy, and technology more than a century after its discovery. Planck's constant stands as a testament to the power of human curiosity and intellectual courage. It reminds us that profound truths often emerge from careful observation, bold theoretical innovation, and the willingness to question the most deeply held assumptions. By introducing HHH, Planck provided humanity not only with a mathematical tool, but also with a new lens through which to view the universe, a lens that continues to reveal the intricate and discrete beauty of the natural world. Max Planck's revolutionary ideas did more than solve the immediate problem of blackbody radiation. They laid the foundation for the entire edifice of modern physics. One of the most remarkable aspects of Planck's work is how it inspired subsequent generations of physicists, including Albert Einstein, Niels Bohr, and Werner Heisenberg, to explore realms of nature previously thought inaccessible. These scientists built upon Planck's concepts, transforming quantum theory from a mathematical solution to a comprehensive understanding of atomic and subatomic phenomena. Planck himself initially introduced the quantum hypothesis cautiously. When he proposed that energy is emitted or absorbed in discrete quanta, he treated it primarily as a formal tool to fit the Blackbody radiation data, rather than a radical reinterpretation of reality. Nevertheless, the implications of his idea were so profound that it immediately caught the attention of the broader scientific community. Planck's work provided the first concrete evidence that the microscopic world obeyed rules fundamentally different from classical physics, opening a doorway that others would eagerly explore. Albert Einstein, one of the most influential physicists of the 20th century, was directly inspired by Planck's quantum hypothesis. In 1905, Einstein applied Planck's concept of energy quanta to light itself, proposing that light consists of discrete particles, later called photons. This groundbreaking idea explained the photoelectric effect, in which electrons are ejected from metals when illuminated by light of sufficient frequency. Classical wave theory could not account for why the energy of ejected electrons depended on light frequency rather than intensity, but Planck's quantization provided the answer. Each photon carries a specific quantum of energy proportional to its frequency. E equals h nu E equals h backslash nu E equals h nu. Einstein's work earned him the Nobel Prize in Physics and demonstrated how Planck's ideas could be generalized to phenomena beyond thermal radiation, influencing the study of light, energy, and matter. Niels Bohr also drew inspiration from Planck's discovery, particularly in his development of the atomic model. At the time, the structure of the atom was a mystery. Classical physics suggested that electrons orbiting a nucleus would radiate energy continuously and spiral into the nucleus, a catastrophic instability not observed in nature. Bohr solved this problem by introducing quantized electron orbits, directly borrowing from Planck's notion of discrete energy levels. In Bohr's model, electrons could occupy only specific orbits, and energy was absorbed or emitted in discrete amounts when electrons transitioned between these orbits. Planck's constant, hhh, provided the precise scale for these energy transitions. Bohr's model successfully explained the discrete spectral lines of hydrogen and validated the concept that the quantum nature of energy governs the behavior of matter at atomic scales. Werner Heisenberg, a later pioneer of quantum mechanics, was similarly influenced by Planck's groundbreaking work. Heisenberg's formulation of matrix mechanics in the 1920s relied on the concept of quantized energy levels and transitions. The mathematical formalism he developed directly incorporated Planck's constant as a fundamental scale, reflecting the granularity of energy and the limitations it imposes on measurement. Heisenberg's uncertainty principle, which defines the fundamental limits of simultaneously knowing a particle's position and momentum, is expressed in terms of hhh, showing that Planck's discovery governs the very foundations of quantum mechanics. Without Planck's initial insight, the rigorous mathematical frameworks of quantum mechanics that Heisenberg and others developed might never have been conceived. The influence of Planck extends beyond these individual scientists. His work created a conceptual shift that transformed the entire scientific landscape. Before Planck, classical physics dominated the world, emphasizing continuity, determinism, and predictability. Planck introduced the radical idea that the microscopic world operates according to discrete, quantized rules. This principle challenged every assumption about the nature of matter, energy, and radiation. Future physicists were compelled to reconsider the foundations of their disciplines, opening the door to novel theories that could describe the atomic and subatomic worlds. Planck's work demonstrated that bold, well-supported theoretical ideas could redefine the trajectory of science, inspiring his contemporaries and successors to explore new intellectual frontiers. Planck's influence was not limited to theoretical breakthroughs. It also shaped the methodology of modern physics. His careful combination of empirical observation and mathematical formalism set a precedent for how to tackle fundamental problems in science. Einstein, Bohr, and Heisenberg all followed this model. They grounded their theories in experimental evidence while extending the conceptual framework to explain phenomena that classical physics could not. Planck's approach, balancing respect for experimental data with willingness to challenge prevailing assumptions, became a guiding principle for the development of quantum theory. The inspiration Planck provided is also evident in the diversity of applications his work enabled. From explaining atomic spectra and the photoelectric effect to laying the groundwork for nuclear physics, quantum chemistry, and quantum field theory, his ideas were a catalyst for discoveries that spanned decades. Einstein, Bohr, and Heisenberg each used Planck's insights to address different scientific problems, demonstrating the versatility and enduring relevance of his contributions. The fact that one theoretical innovation, energy quantization, could generate such a wide array of breakthroughs underscores the depth and significance of Planck's work. Moreover, Planck's influence was not solely scientific. It was cultural and philosophical. By challenging classical assumptions, he encouraged a mindset that embraced uncertainty, probability, and the limits of human knowledge. Einstein's work on relativity and quantum theory, Bohr's complementarity principle, and Heisenberg's uncertainty principle all reflect this philosophical shift. Planck's introduction of quanta forced scientists to accept that the universe operates on principles fundamentally different from everyday intuition, inspiring generations to rethink reality itself. In practical terms, the legacy of Planck's influence can be seen in countless technological advancements. The quantum mechanics developed by Einstein, Bohr, and Heisenberg underpins semiconductors, lasers, quantum computing, and medical imaging, among many other technologies. Each of these innovations traces its intellectual ancestry to Planck's first insight into the discrete nature of energy. By inspiring these scientists, Planck set in motion a chain of discoveries that not only expanded human understanding, but also transformed the way we live, communicate, and interact with the world. Max Planck is celebrated not only for his groundbreaking contributions to physics, but also for his extraordinary resilience and unwavering dedication to science, even in the face of personal tragedy, political turmoil, and societal upheaval. While his intellectual achievements, such as the introduction of quantum theory and Planck's constant, have profoundly shaped the scientific world, the human qualities that enabled these breakthroughs are equally remarkable. Planck's story demonstrates that scientific progress is not just a product of genius. It is also the result of perseverance, discipline, and moral courage in confronting challenges both inside and outside the laboratory. Born in 158 in Kiel, Germany, Planck was raised in an intellectually nurturing environment. His father was a law professor, and his family valued rigorous thinking and education. From an early age, Planck exhibited a deep curiosity about nature and mathematics, displaying a disciplined approach to learning that would characterize his entire career. He pursued physics with passion, studying under some of the most eminent scientists of his time. His early work, focused on thermodynamics and electromagnetism, laid the foundation for his later revolutionary ideas. Despite his innate brilliance, Planck faced immense challenges throughout his life. The scientific environment in late 19th century Germany was highly competitive, dominated by classical physics and a strong adherence to established theory. Introducing radical concepts such as energy quanta required not only intellectual acuity but also courage. Planck's peers were skeptical, and many initially resisted his ideas. Unlike more flamboyant innovators, Planck approached his revolutionary work with careful deliberation, a methodical mindset, and humility. He balanced bold theoretical insight with rigorous attention to experimental data, demonstrating that resilience in science often involves patience and prudence as much as creativity. Planck's personal life was marked by profound tragedy, which tested his resilience in ways few scientists experience. He lived through both world wars, witnessing the devastation, social upheaval, and political chaos that gripped Germany. During this period, Planck endured the loss of several close family members. In 1937, his beloved son Erwin was executed by the Nazi regime for his involvement in the resistance against Hitler, an event that caused Planck immense grief. Despite this devastating personal loss, he continued his work in physics and remained committed to the pursuit of knowledge. Planck's ability to persevere through such hardship exemplifies the human strength behind scientific progress, the emotional fortitude required to continue inquiry amid overwhelming challenges. Planck's resilience was also evident in his dedication to the scientific community and intellectual integrity. He maintained a lifelong commitment to teaching, mentoring, and supporting young physicists. He fostered an environment that encouraged rigorous debate and experimentation, recognizing that the progress of science depends on collaboration, mentorship, and the free exchange of ideas. Even as he navigated the challenges of war, political oppression, and personal tragedy, Planck remained an active participant in the international scientific dialogue, emphasizing reason, evidence, and ethical responsibility over personal gain or recognition. In addition to personal resilience, Planck's dedication to science can be seen in the painstaking rigor with which he developed his theories. His work on blackbody radiation and the quantum hypothesis required extraordinary attention to detail, combining experimental results with mathematical formalism. He spent years refining his ideas, carefully ensuring that they fit observations while preserving theoretical consistency. This methodical approach highlights a critical aspect of scientific progress. Breakthroughs rarely occur instantaneously or without discipline. Planck's dedication to precision and accuracy allowed him to propose revolutionary concepts without abandoning scientific rigor, setting a standard for future generations of physicists. Planck's perseverance also contributed to the acceptance and expansion of his ideas. Initially, the notion of energy quanta was controversial, met with skepticism from many leading scientists. Planck himself did not claim all the implications of his theory immediately. He introduced quantization cautiously, presenting it as a mathematical tool rather than a radical reinterpretation of nature. Over time, however, the undeniable accuracy of his formulas and the conceptual power of his hypothesis gained recognition, influencing the work of Einstein, Bohr, Heisenberg, and others. Planck's dedication to careful reasoning, even in the face of doubt, demonstrates that resilience is not simply stubbornness. It is the ability to combine patience, intellectual integrity, and steadfast pursuit of truth. Furthermore, Planck's human qualities remind us that scientific progress is deeply intertwined with ethical and moral considerations. He lived through a period of extreme political pressure, including the rise of the Nazi regime in Germany. Despite the dangerous climate, Planck attempted to protect colleagues and preserve scientific integrity, advocating for rational discourse and resisting the politicization of science. His commitment to principles, even when it was personally risky or emotionally taxing, illustrates that the human side of scientific progress encompasses moral courage as well as intellectual dedication. Planck's resilience and dedication have had a lasting impact on the culture of science. His approach demonstrated that groundbreaking discoveries are not solely the product of flashes of genius. They require sustained effort, the ability to cope with failure and criticism, and the perseverance to continue in the face of adversity. This lesson has inspired countless generations of scientists who recognize that persistence, integrity, and emotional fortitude are as crucial to discovery as creativity and intelligence. The human side of Planck's work also underscores the relationship between personal character and scientific achievement. His humility, patience, and ethical approach allowed him to introduce ideas that would revolutionize physics without alienating the scientific community. He served as a model for how scientists can navigate intellectual controversy, personal loss, and societal upheaval while remaining committed to the pursuit of truth. In this way, Planck's life illustrates that the progress of science is inseparable from the qualities of the individuals who advance it. Max Planck's contributions to science extend far beyond the momentous discovery of energy quanta. They constitute a legacy that continues to influence modern physics, technology, and our understanding of the universe. His pioneering work in quantum theory not only resolved immediate scientific puzzles, such as blackbody radiation, but also laid the foundation for subsequent breakthroughs that define contemporary physics. From the formulation of quantum mechanics to cutting-edge technologies, Planck's intellectual impact persists, reflecting both the power of his ideas and the lasting significance of his scientific vision. Planck's discovery of the quantization of energy revolutionized the way scientists perceive nature. Before Planck, classical physics assumed that energy could vary continuously, applying these principles to light, heat, and matter. Experiments, however, increasingly demonstrated phenomena that classical theory could not explain. The ultraviolet catastrophe, the discrete spectra of atoms, and the photoelectric effect all indicated the limitations of classical models. By introducing energy quanta and Planck's constant HHH, Planck provided a new framework that could account for these anomalies and, crucially, opened the door to a fundamentally different view of the microscopic world. The direct legacy of Planck's work is evident in the development of quantum mechanics, one of the two pillars of modern physics alongside general relativity. Quantum mechanics builds upon Planck's initial insight that energy is discrete, expanding it into a comprehensive mathematical and conceptual framework. Scientists such as Einstein, Bohr, Heisenberg, Schrödinger, and Dirac extended Planck's ideas to explain phenomena ranging from atomic structure to subatomic particle interactions. Every quantum equation, from Heisenberg's uncertainty principle to Schrödinger's wave equation, traces its roots to Planck's introduction of discrete energy packets. In this sense, Planck's work serves as the cornerstone upon which the modern understanding of matter and energy is constructed. Beyond theory, Planck's legacy profoundly shapes technology. Quantum mechanics, born from his ideas, underpins the operation of semiconductors, which are the foundation of computers, smartphones, and nearly all modern electronics. Lasers, used in communications, medicine, and manufacturing, rely on energy transitions that are quantized according to Planck's principles. Even medical imaging technologies such as MRI and PET scans are predicated on quantum phenomena, which owe their theoretical basis to Planck's early discoveries. These applications illustrate how abstract theoretical insights can translate into transformative real-world technologies, profoundly impacting society. Planck's influence also extends to the realm of metrology and standards. Planck's constant has become a fundamental reference for the measurement of physical quantities. In 2019, the International System of Units (C) redefined the kilogram in terms of Planck's constant, replacing the historical physical artifact with a universal constant of nature. This milestone highlights the enduring practical significance of Planck's work. A discovery made over a century ago now underpins the very standards by which we measure mass, energy, and physical quantities globally. The philosophical and conceptual legacy of Planck's work is equally profound. By introducing quantization, Planck challenged the deterministic worldview of classical physics, revealing a universe governed by discrete events and probabilistic principles at microscopic scales. This insight transformed not only scientific thought, but also philosophical interpretations of nature. The recognition that reality at its most fundamental level is quantized has influenced fields as diverse as chemistry, materials science, cosmology, and even information theory. Planck's ideas forced scientists to adopt a mindset that embraces uncertainty, complexity, and the limits of intuition, fostering a culture of intellectual curiosity that continues to drive discovery. Planck's legacy is also evident in the educational and research institutions that carry forward his influence. Universities, research centers, and laboratories worldwide teach quantum theory as a central component of physics curricula, ensuring that generations of students learn not only the mathematical formulations but also the conceptual insights pioneered by Planck. Research in quantum computing, nanotechnology, particle physics, and quantum cryptography builds directly upon the principles he introduced. In this way, Planck's contributions continue to shape the intellectual development of scientists, engineers, and innovators across disciplines. Moreover, Planck's life and work serve as an enduring example of scientific integrity and perseverance. Despite personal tragedies, including the loss of family members and the upheavals of 2 world wars, Planck remained dedicated to the pursuit of knowledge and the advancement of physics. His meticulous, patient approach to problem solving, combined with moral courage and ethical conduct, provides a model for how scientists can navigate both intellectual and personal challenges. This human aspect of his legacy reinforces the idea that science is not only a pursuit of abstract truths, but also a deeply human endeavor shaped by character, resilience, and dedication. Planck's influence even extends into contemporary scientific frontiers, including quantum computing and quantum information theory. The principles of quantization, superposition, and discrete energy levels first introduced by Planck form the theoretical backbone of technologies that promise to revolutionize computation, secure communications, and data processing. These emerging fields exemplify the forward-looking nature of Planck's contributions, demonstrating that his insights continue to generate new possibilities more than a century after their introduction. Finally, Planck's legacy reminds us of the cumulative and collaborative nature of science. While he originated the quantum hypothesis, its full implications were realized through the work of Einstein, Bohr, Heisenberg, Schrödinger, and countless others. Planck's ideas acted as a catalyst, inspiring further exploration and innovation. This interplay between foundational insight and collaborative development illustrates how scientific revolutions emerge, not from isolated genius alone, but from the combination of visionary ideas and collective intellectual effort.